Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. In this video lecture we are going to discuss how to find the value of particular integral of linear differential equation with constant coefficient when the right hand side value of equation is exponential function, that means of the type e raised to ax. Then before going to the particular integral of this type, so let's revise the thing which we learned in our previous video lecture called complementary function. So we know that in briefly we are writing a linear differential equation with constant coefficient as f of d times y is equal to capital X, and this equation has two type of solution. First is called as complementary function and second is called as particular integral. So complete solution is the sum of complementary function and particular integral. So now in the previous video lecture we discuss and solve some examples related to the complementary function of the linear differential equation. So now let's try to discuss about how to find the value of particular integral. So before going to solving the example on this particular integral, let's first define the particular integral. Since we know that in brief we can write linear differential equation with constant coefficient as f of d times y is equal to capital X, then particular integral can be written as 1 upon f of d into x, and its notation we can denote this as Pi, or some people may write this as yp. Yp stand for particular integral. So this is the notation to denote the particular integral, 1 upon f of d into x. So then to find 1 upon d into x, we define 1 upon f of d as the inverse operator of f of d, and second note is that 1 upon f of d into x is defined as that function of x which when operated upon f of d gives x. So now all of we know that particular integral is equal to 1 upon f of d into x. Then here the value of capital X is a function of small x, or sometime it may be constant. Then again question arises that, so what is the meaning of function of small x? Actually function of small x means capital X may be exponential function of the type e raised to ax, capital X may be sine of ax or cos of ax, that means trigonometric function, or capital X may be of the type x raised to n, that means algebraic function. Capital X may be combination of exponential function with trigonometric function and algebraic function, that means capital X is equal to e raised to ax into v, where v is either sine of ax, cos of x, or x raised to n. So capital X may be x into v, where power of x is 1 and v may be trigonometric function like sine of ax or cos of x. Capital X may be x raised to n into v, where power of x is greater than 1 and v is a trigonometric function either sine of ax or cos of ax. And last type of the value of capital X is either tan of ax, cot of x, sec of ax, cosec ax, x raised to e raised to x, sine of e raised to x, cos of e raised to x, or 1 upon 1 plus e raised to x, and other values. So in general, so there are 7 different types of values of x are available on the right hand side of linear differential equation with constant coefficient. So this is the general idea about the types of values of capital X. So in detail we are learning all these 7 types for finding the value of particular integral. So depending upon the types of value of x, we get different types of particular integral. So in this presentation, so we are discussing the type first. So how to find the value of particular integral when the right hand side of linear differential equation with constant coefficient, that is capital X is equal to e raised to ax, that is exponential function. So these methods are called as the shortcut methods for finding the value of particular integral of certain standard cases. So now whenever value of capital X is e raised to ax, then the value of particular integral is given by, so particular integral is equal to 1 upon f of d e raised to ax is equal to 1 upon f of a e raised to ax. So this is possible only when the value of denominator term f of a is not equal to 0. So first try to understand the meaning of this particular integral. So here whenever d term is there, so replace d by a, where a is obtained from the term e raised to ax. So now replace d by a. So this is the meaning of this particular integral. Then it may possible that denominator term may get 0, so when we replace d by a. So whenever we get denominator term as 0 when we replace d by a, in this case attach x on numerator and take the derivative of denominator with respect to d. So now if we attach x, then we get this as x upon f dash of a into e raised to ax. Again here this condition is happened provided that the value of f dash of a is not equal to 0. So if once again if the value of f dash of a is 0, then attach one more x on numerator and take the second derivative of denominator with respect to d, and we can continue this formula. So this is the type 1 for finding the value of particular integral of the linear differential equation when the right hand side is exponential function. So now along with this type number 1, let's try to understand some notes. So question may get arise in the student mind that, so how long we have to find the value of particular integral, or how long we have to solve the example so that we can get the value of particular integral. So answer to this question is that, so if the denominator reduces to constant term, so then we are reaching the complete particular integral of the given equation. So that means denominator is free from the operator d. Then in some questions it may possible that we may get constant term on the right hand side. So whenever we get the constant term on right hand side, then replace constant term k, suppose any constant, so we are denoting this constant by k, so replace constant by k into e raised to 0x. That means we get the value of a as 0. Then replace the operator d by 0, or replace constant by we get the constant value. Then here example is 1 upon f of d into k e raised to 0x is equal to 1 upon f of 0 k into e raised to 0x. So again this is happen only when the denominator is not equal to 0. So if a raised to x type of terms are there, then we write this a raised to x as e raised to x into log of a. So thus for a raised to x we can replace d by log of a. So f of 1 upon f of d a raised to x is equal to 1 upon f of log of a raised to x. So here we are replacing d by log of a. That means whenever a raised to x term is there, so then replace d by log of a. So then for learning this type number 1, we required some basic results. So these basic results related to this type number 1 is hyperbolic sin hx. That means sin hx is equal to e raised to x minus e raised to minus x upon 2, and hyperbolic cos function is equal to e raised to x plus e raised to minus x upon 2. And for solving example based on this type number 1, so we may replace constant term by k as k is equal to k into e raised to 0x. Whenever a raised to x term is there, then we can write a raised to x as e raised to x into log of x. So these are the some important things about this type number 1. So now let's discuss the first example, or let's start try to solve the example of linear differential equation which is based on type number 1. So now here example is solve the linear differential equation with constant coefficient as d square minus 7d plus 12 into y is equal to e raised to 2x. We know that this is linear differential equation with constant coefficient. This equation has two type of solution. First is called as complementary function, and second is called as particular integral. So here if we try to find the value of complementary function, then again we know that complementary function is obtained by solving the auxiliary equation. So here the value of auxiliary equation is d square minus 7d plus 12 is equal to 0. So according to the quadratic root formula, so we can find the root of this equation which are 3 and 4. So if we observe these roots, then these roots are real and non-repeated. So as the roots are real and non-repeated, then according to the complementary function formula for finding the real and non-repeated roots, so here the complementary function is equal to c1 e raised to 3x plus c2 e raised to 4x. This is happen because of the standard formula of complementary function when roots are real and non-repeated. So let's assume that this is your equation number 1, which is the first solution, which is called as complementary function. Now let's try to find the value of particular integral. So whenever we are finding the value of particular integral of any linear differential equation with constant coefficient, so first write down the value of right hand side of linear differential equation, so which is denoted by capital X. Now here the right hand side value of linear equation is e raised to 2x. So if we compare this value with the type capital X is equal to e raised to ax, so which is our first type for finding the value of particular integral, so then we get the value of a as 2. So that means we can replace d by 2. Then according to the particular integral formula, so we can write this as 1 upon f of d e raised to ax is equal to 1 upon f of a e raised to ax. So that means replace d by a. So here particular integral is equal to 1 upon f of d. So value of f of d is d square minus 7d plus 12. So into e raised to 2x. So which is equal to, so replace d by 2. So value of d by 2, that means d by a. So value of a is 2. So now d replace 2, so we get this as 2 square minus 7 into 2 plus 12 into e raised to 2x. So if we try to simplify the value of denominator, then we get the value of denominator as 1 upon 2 into e raised to 2x as it is. So in this way we get the value of particular integral of the linear differential equation. Let's denote this equation by b. So from equation a and b, so we get the complete solution of the given equation, which is the sum of complementary function and particular integral. So complete solution is denoted by y, which is equal to c1 e raised to 3x plus c2 e raised to 4x plus particular integral as 1 upon 2 e raised to 2x. So this is the first example, which is very simple to understand the type 1 of linear differential type 1 of finding particular integral of the linear differential equation. Now let's discuss the example number 2. So now example number 2 is, suppose solve third derivative of y with respect to x minus 3 times second derivative of y with respect to x plus 4y is equal to e raised to 3x. So we mentioned this example in terms of derivative. So if we apply the operator d, so d means derivative with respect to x, so to this equation, then we can convert the given equation in with the help of operator d as d cube minus 3d square plus 4, then we are taking y common, is equal to e raised to 3x. So observe that this is cubic equation. So we can easily solve this cubic equation with the help of synthetic division method. So now first try to write down the equation in decreasing power of d. So d cube d square, d term is absent, so coefficient of d is 0. So coefficient of these equations are 1, minus 3, 0 and 4. So now try to find out the factors of this equation. So d is equal to minus 1 is the factor when the sum of alternative coefficient is 1. So sum of 1 and 0 is 1, and sum of minus 3 and 4 is 1. So sum of alternative coefficient is 1. That means d is equal to minus 1 is the factor. So let's try to solve the cubic equation by factor d is equal to minus 1. So 1 as it is, 1 into minus 1, we get this as minus 1. So minus 3 minus 1 sum is minus 4. Again, product of minus 1 and minus 4 is 4. Minus minus become plus. Then sum of 1 and sum of 0 and 4 is 4. So again, product of minus 1 and 4 is minus 4. So 4 and minus 4, its sum is again 0. So here the value of the remainder is 0. That means d is equal to minus 1 is the factor. So let's write down this in terms of factor as d minus, write down the opposite sign, d plus 1. So then remaining terms are d square minus 4d plus 4. Again, second bracketed equation is quadratic equation. So we know the method of solving the quadratic equation. So if we factorize this term, then we get factor as d plus 1, d minus 2 is equal to 0. So if we try to simplify this for the value of d, then we get the value of d as minus 1, 2 and 2. So this is one of the method which is called as synthetic division method for solving the cubic equation. So this example is also solvable with the help of another method. So instead of minus 3d square, we can split this minus 3d square into two parts. So that we can easily convert this function in terms of factor. And again, if we add plus 2d and minus 2d, and after taking some term common, we are getting the same factor as that of the synthetic division method. And again, we get the same root, so which are minus 1, 2 and 2. So these roots are real and repeated, and according to the standard formula for finding the value of complementary function. So complementary function is c1 e raised to minus x plus 2 term is repeated twice, so c2 plus c3x e raised to 2x. So this is equation 1, which is called as complementary function of the equation. Now let's find out the value of particular integral of the given equation. So now we know that whenever we find the value of particular integral of any equation, so first try to write down the right hand side of the linear differential equation. So here the right hand side value of linear equation is e raised to 3x, which we are denoting by capital X. So if we compare this value with our standard formula type number 1, capital X is equal to e raised to ax, then we get the value of a as 3. So then according to the type 1 formula for finding the value of particular integral, when x is equal to exponential function, then particular integral is equal to 1 upon f of d e raised to ax is equal to 1 upon f of a e raised to ax. If we apply this formula to the given example, then value of f of d is d cube minus 3d square plus 4 into e raised to 3x. So then replace d by a according to the type number 1 formula. So we can write this as value of a is 3. So 3 cube minus 3 into 3 square plus 4 into e raised to 3x. So if we simplify this denominator carefully, then we get the value of denominator as 4. So that means from denominator d term is absent. As d term is absent from the denominator, that indicate that we got the value of we got the value of particular integral of the given equation. So now here the value of particular integral is e raised to 3x upon 4. So if we combine the value of complementary function and particular integral of this equation, then we get the value of complete solution, which is c1 e raised to minus x plus c2 plus c3x e raised to 2x plus particular integral e raised to 3x upon 4. So this is the second example. So this is simple and important example for understanding the type number 1 for finding the value of particular integral while solving the linear differential equation with constant coefficient. Now let's discuss example number 3. So now here example number 3 is third derivative of y with respect to x plus 3 times second derivative of y with respect to x plus 3 times derivative of y with respect to x plus y equal to e raised to minus x. So now if we apply the operator d, which means derivative with respect to x, so we can easily convert the given example in terms of d cube plus 3d square plus 3d plus 1 into y is equal to e raised to minus x. So we know that this is a cubic equation. So this equation has two type of solution, complementary function and particular integral. So let's first find out the value of complementary function. Again, we know that complementary function is obtained by solving the auxiliary equation. So now here the value of auxiliary equation is d cube plus 3d square plus 3d plus 1 equal to 0. So we know that this is cubic equation, so we can solve cubic equation with the help of synthetic division. So this equation is always in decreasing power of d, so write down the coefficient of d, which are 1, 3, 3 and 1. So now d is equal to minus 1 is the factor when the sum of alternative coefficient is equal. So here the sum of alternative coefficient is 1 and 3, again 1 and 3, so which is 4, which is same for both the coefficient. That's why d is equal to minus 1 is the factor. So now keep 1 as it is. So 1 into minus 1 we get as minus 1. So 3 minus 1 answer is 2 sum. Then 2 into minus 1, so we get answer as minus 2. So 3 into minus 2 we get some answer as 1. Again 1 into minus 1 we get value as minus 1. So 1 and minus 1 is 0, so we get remainder value as 0. So when we get remainder as 0, that means d is equal to minus 1 is the factor of the given cubic equation. Now let's simplify this equation once again. So we get factor as d plus 1 into d square plus 4d plus 1. So then if we once again factorize this term according to the quadratic form, then we get this as d plus 1 and d plus 1. That means this factor is repeated thrice. So we get the value of root of this equation as minus 1 and minus 1. So this is one of the method for solving the cubic equation, which is called as synthetic division method. And a second alternative method for solving the given example is that, so given example is in the standard form of d plus 1 its cube. So if we expand the term d plus 1 its cube, then we get the answer as d cube plus 3d square plus 3d plus 1 equal to 0. So again we get the same factor and we get the unique value for the root of this equation, which are minus 1 for 3 times. So now, so these roots are real and repeated because minus 1 is repeated thrice. So now according to the standard formula for finding the value of complementary function, so value of complementary function is c1 plus c2x plus c3x square into e raised to minus x. Let's denote this equation by capital A, so which is the value of our complementary function of the given equation. So now next step is to find out the value of particular integral. Whenever we find the value of particular integral of any equation, so first write down the value of right hand side term. So here the right hand side term value is e raised to minus x, which is denoted by capital X. So if we compare this value with our standard type x is equal to e raised to ax, then we get the value of a as minus 1. So then according to the type 1 formula for finding the value of particular integral, so particular integral is 1 upon f of d. So value of f of d is d cube plus 3d square plus 3d plus 1 into e raised to minus x. So replace d by a. So value of a is minus 1. So minus 1 its cube plus 3 into minus 1 square plus 3 into minus 1 plus 1. So if we try to simplify the value of denominator term, then we get the value of denominator as 0. And we know that whenever we get 0 term in the denominator, then attach x on numerator and take the derivative of denominator with respect to d. So we get this term as x upon 3d square plus 60 plus 3 into e raised to minus x. So that means after taking the derivative of d cube plus 3d square plus 3d plus 1 term. So now once again try to replace d by a. Value of a is minus 1. Then we get next step as x upon 3 into minus 1 square plus 6 into minus 1 plus 3 into e raised to minus x. So once again if we try to simplify the value of denominator term, then again we get the value of denominator term as 0. So once again apply the same formula. Whenever we get 0 term in the denominator, Then attach x on numerator and take the derivative of denominator. So x into x square. So derivative of 3d square plus 6d plus 3 is 6d plus 6. So it's derivative. Then once again apply the formula, that means replace d by a, where the value of a is -1. So we get this as x square upon 6 into bracket -1 plus 6. So once again the value of denominator term is 0. That means third time we got the value of denominator as 0. So now again attach one more x on the numerator and take the derivative of denominator. So x into x square, we get numerator value as x cube upon derivative of the term 6d plus 6 is 6 into e raised to minus x. So after doing this step, so there is no d term is available in the denominator as well as in numerator. That means we reach to the final solution of particular integral. So in this way we can easily find out the value of particular integral, and we are denoting this by equation B. So if we combine these two solutions together, then we get the value of complete solution, so which is given as y is equal to c1 plus c2x plus c3 x square e raised to minus x plus x cube upon 6 e raised to minus x. So now let's discuss the example number 4. Slowly we are going towards the typical examples or tough type of example. Now example number 4 is second order derivative of y with respect to x minus y equal to 1 plus e raised to minus x raised to its square. That means 1 plus e raised to minus x square. So now first find out the value of complementary function. So here the value of auxiliary equation is d square minus 1 equal to 0. That means we get the factor as d minus 1 and d plus 1. So according to the rule, a square minus b square is equal to a plus b and a minus b. So the value of t is minus 1 and minus 1. So observe that these roots are real and non-repeated. So according to the complementary function formula, so value of complementary function is c1 e raised to minus x plus c2 e raised to x. So this is our equation number 1, so which is called as the complementary function of the given equation. Now let's find out the value of particular integral. So here the right hand side value is 1 plus e raised to minus x its square. So this equation is not in our standard form. So first try to convert the given equation in terms of standard form. So if we make the square of this equation, then we get this term as, so because we are applying the formula a plus b its square, which is a square plus 2 times ab plus b square. So now here the value of 1 square is 1 plus 2 times 1 into e raised to minus x, which is e raised to minus x, plus b square, that means e raised to minus x its square, we get the value as e raised to minus 2x. So after simplification of this term, we get the right hand side term in the standard form. That means if we replace 1 by 1 into e raised to 0x, second term as it is, third term as it is, then we get all the three term, that means e raised to 0x, 2 e raised to minus x and plus e raised to minus 2x. All these three terms are in standard form. That means we get standard form type number 1 when x is exponential function. So then we can easily apply type number 1 for solving the example. So if we write the formula for particular integral, then 1 upon f of d. So value of f of d is d square minus 1 into capital X, which is e raised to 0x plus 2 e raised to minus x plus e raised to minus 2x. So on the right hand side there are three terms. So let's split these three terms into three parts. So first part is 1 upon d square minus 1 e raised to 0x, middle sign is plus 1 upon d square minus 1, 2 is constant, write down as it is, e raised to minus x. Again in between two term plus sign is there, so plus 1 upon d square minus 1 into e raised to minus 2x. So you may separately solve the first term, second term and third term and combine all these three answers together, and you will get the final value for particular integral. Or second method is that we may solve this equation simultaneously for all three terms. So now in first term the value of a is 1 because e raised to 0x. So replace d by 0. we get this as 0 square minus 1 e raised to 0x, plus in second term, so value of a is minus 1. So replace d by minus 1. So minus 1 square minus 1 into 2 e raised to minus x, plus in third term, so value of a is minus 2, that means replace d by minus 2. So we get this as minus 2 its square minus 1 into e raised to minus 2x. So if we simplify the denominator of first term, then we get the value of denominator of first term as minus 1. So we take that minus 1 in the numerator. Plus if we simplify the denominator of second term, then denominator of second term becomes 0, because plus 1 and minus 1 is 0. So whenever we get 0 term in the denominator, so in that case attach x on numerator and take the derivative of denominator. So derivative of d square minus 1 is 2d. So that's why denominator is 2d into 2 e raised to minus x as it is, plus if we discuss about term number 3. So if we expand the term number 3, then we get the value of denominator as 1 upon 3 e raised to minus 2x. So here first term in first term and third term, so d term is absent, only d term is present in the second term. So let's remove the d in second term with the help of operator. With the help of the term, replace d by a. So we can write next step as minus e raised to 0x plus x by 2 as it is. So replace d by minus 1. So we get this as minus 2 in the denominator into 2 e raised to minus x as it is, plus third term as it is 1 upon 3 e raised to minus 2x. So finally we get the answer for particular integral as minus 1, because e raised to 0x is 1. Minus 2 will get cancelled, so minus x into e raised to minus x plus 1 upon 3 e raised to minus 2x. So if we combine the value of complementary function and particular integral, then we get the value of complete solution as c1 e raised to minus x plus c2 e raised to x minus 1 minus x e raised to minus x plus 1 upon 3 e raised to minus 2x. So this is the fourth example. So with the help of this four example, we can easily solve any example which is based on type number 1 for finding the value of particular integral. Now let's discuss one more example about type number 1. So solve the equation d cube minus 5d square plus 8d minus 1y equal to e raised to 2x plus 2 times e raised to x. So if we try to find the value of complementary function, then auxiliary equation is d cube minus 5d square plus 8d minus 1 equal to 0. We know that this is cubic equation, so apply the synthetic division method. So first write down the d term in decreasing power of d, so all are in decreasing power of d. So coefficient of cubic equations are 1, minus 5, 8 and minus 4. So here if we try to find the value factor of this equation for d is equal to minus 1. So when the d is equal to minus 1 is the factor, if the sum of alternative coefficients of cubic equation is equal, so if we take the sum of alternative coefficient, then sum of first and third coefficient is 1 plus 8, that means 9. And sum of next alternative coefficient is minus 5 and minus 4, which is minus 9. That means plus 9 and minus 9 are not equal. That indicate that d is equal to minus 1 is not the factor. So let's try to find out the next factor. Next factor is d is equal to plus 1. So d is equal to plus 1 is the factor of cubic equation when the sum of all coefficients is 0. If we take the sum of all coefficients, then we get this sum as 1 minus 5 plus 8 minus 4, which is 0. That means d is equal to 1 is the factor. So let's try to solve this equation with the factor d is equal to 1. So first term 1 as it is. 1 into 1 is 1. So sum of minus 5 and 1 is minus 4. Again product of minus 4 and 1 is minus 4. If we take the sum of 8 and minus 4, we get answer as 4. Again product of 4 and 1 is 4, and the sum of minus 4 and 4 is 0. So we get remainder value as 0. So whenever we get remainder as 0, that means d is equal to 1 is the factor. If we simplify this, then we get d minus 1, d square minus 4d plus 1 equal to 0. So after simplification with the help of quadratic equation, we get the root of this equation as 1, 2 and 2. So these roots are real and 2 roots are repeated. That means 2 is repeated twice. So we can write complementary function as c1 e raised to x plus c2 plus c3x e raised to 2x. So this is our first equation denoted by a. Now let's find out the value of particular integral. So here the value of right hand side is e raised to 2x plus 2 times e raised to x. So if we observe this equation carefully, then the value of right hand side is in our standard form of type number 1, capital X is equal to e raised to x. For the value of a, in the first term value of a is 2, whereas the value of a is equal to 1 in the second term. So if we try to find the value of particular integral, then particular integral is equal to 1 upon f of d, which is d cube minus 5d square plus 8d minus 1 into e raised to 2x plus 2 e raised to x. So right hand side is the sum of two exponential function. So let's split the right hand side into two terms. So 1 upon d cube minus 5d square plus 8d minus 4 into e raised to 2x plus second term 1 upon d cube minus 5d square plus 8d minus 4 into 2 e raised to x. That means we split the given equation into two parts, and middle sign is plus because in between e raised to 2x and 2 e raised to x there is plus sign. So you may solve first term and second term independently, or you may solve these two terms simultaneously. So in first term replace d by 2, and in second term replace d by 1. So in both the cases, when we replace d by 2 in first term and d is equal to 1 in second term, so we get the denominator for both the term as 0. Whenever we get denominator term as 0, then multiply numerator by x and take the derivative of denominator. So we get next step as x upon derivative of d cube minus 5d square plus 8d minus 4 is 3d square minus 10d plus 8 into e raised to 2x plus again same, attach x on numerator and derivative of denominator into 2 e raised to x. So then next step is again replace d by a. In the first term value of a is 2, so replace d by 2. Again in a second step the value of a is 1, so replace d by 1 and simplify. So if we try to simplify the first term, then the value of first term is again 0, whereas the value of second term is, denominator of second term is 1. So the role of second term is over because in the second term d term is not available. So only we have to solve the example for the first term. So whenever we get the denominator as 0, so once again attach x on numerator and take the derivative of denominator. So x into x, x square, and derivative of 3d square minus 10d plus 8 is 6d minus 10. So once again replace d by a. So if we replace d by a, where the value of a is 2, then we get final answer as x square upon 6 to the 12 minus 10, that means 2. That means x square upon 2 e raised to 2x plus 2 into e raised to x. So this is the value of particular integral of the equation. So now if we combine the complementary function and particular integral, then we get the final solution as y is equal to c1 e raised to x plus c2 plus c3x e raised to 2x plus value of particular integral x square by 2 e raised to 2x plus 2x into e raised to x. So in this presentation or in this video lecture, we discuss about the 5 example. So with the help of this 5 example, you may solve any example which is based on type number 1. So where the right hand side is an exponential function. So now some examples are given here for your practice purpose. So solve this example and test your knowledge. So along with these examples, answers are also given. So if you face any difficulty, then you may write for me on the channel. Friends, now this is the time to thanks to you. So thanks for patient listening. So thanks one and all.